In this video, we're going to explore a really interesting property of the divergence theorem. So what I want to begin with is imagine a region, a three-dimensional region, that has an inside surface and an outside surface. For example, imagine a region that has an inside, which is going to be a small sphere, and has an outside, a much larger sphere, something like this. So the region I'm talking about is that volume in between these two spheres. The outer surface of this region is the large sphere, and the inner surface of this region is the small sphere. Perhaps I'll call the inner surface S1 and the outer surface S2. And then I want to consider, from the perspective of this region that's in between these two spheres, the outward normals. Well, on the outer sphere is going to point out, I'll call this N2 for the outward normal on the second surface. And then on the inner surface, the outward normal of the domain I'm talking about, the space between these two spheres, its outward normal would point in towards the origin. And I'll call that N1, the outward normal for the inside surface. And indeed, maybe I'll just shade in here and paint this region, which is in the middle. That's the portion I'm thinking of for my volume. What does the divergence theorem say in this context? So I'd written out already what the divergence theorem was. In general, it talked about the flux across a surface, that is a surface integral of f dot n d sigma, and said that was equal to a volume integral, a triple integral of the divergence. So basically, integrating this differential operator of the divergence over the entire region was just going to give you, well, the flux across the boundary. Now, if I apply that here, the surface that I'm talking about is really an S1 union S2. There's two surfaces here, an inside one and an outside one. So the flux across the surface in general is, well, going to be the sum of these two things. So now I'll just restate the divergence theorem, breaking up the flux across the surface into the two different regions. I'll say that the surface integral over the S1, and then I'm computing the flux, so it's of f dot n d sigma, added to the surface integral along the outside, the S2 of the f dot n d sigma, well, that has to add up to the triple integral over the region of the gradient of f dv. That's our restatement of the divergence theorem in this context. Now, I have to be extremely careful about my normals, though. You'll actually note I wrote just dot n in both cases. I didn't write n1 or n2 yet. I'm going to fix that right now. Because, well, if I think about the outer surface, the S2, the orientation of the normal to is outward from the perspective of this region that I'm considering in between these two things. And then if I was just to consider that flux integral by itself, it would also be outward. The outward flux across that surface, just by itself, would be indeed that N2. So I'm going to come in here and I'll call that f dot N2. So that one's okay. And the N1 is a bit weirder here, because if you'll recall, we had come along and written the N1 pointing inwards. And the reason we had done that was because from the perspective of the region in between these two spheres, if you go out from that region, on the inner surface, it means it's pointing down inwards towards the origin. But if I were just to do this left surface integral over here, and I didn't know anything about the region that was being contained, I would say the outward flux for the inner sphere would be pointing the opposite direction, would be pointing outwards. So that means if I want to write an N1 here, I have to put a negative out the front of it as well, because my N1 is oriented exactly the opposite of how I would do that integral if I was just given that integral and told to do it by myself. I would have thought the outward flux would be going the opposite, the negative of the N1. Okay, so I have this particular formula. Nevertheless, I have this formula here. And then I'm going to note one corollary, which is that if, so it's not always true, but if the divergence was equal to 0, and if that was the case, you would, thus cut the right-hand side from it, then we can state this a little bit more cleanly. This negative sign moves that term to the other side, and what I'm going to have is that the integral over the second surface of f dot n2 d sigma is the integral over the first surface of f dot n1 d sigma. That is, the flux over these two completely different surfaces is exactly the same when the divergence is 0. So this tells us some really nice things. If the divergence is 0, then you in fact can replace any surface that you might have with some surface that's much easier for you to compute. Say your S2 was really big and messy and gnarly and you didn't want to deal with it. Well, if the divergence is 0, The flux across that messy surface could be just the flux across some simple surface that you do know how to compute.